Hello from Fort Collins, Colorado. I'm John Wasson with Wasson-ECE. Today we're going to spend a few moments talking about high quality, high grade ethylene monomer. As we wake up each morning, if we're in the ethylene business, the first thing we think about is trace impurities in our ethylene product. That's going to affect our catalyst, our polymerization process, or if we're selling product in the open market, the price that we can get for that ethylene. What are we going to talk about today? We'll understand the problem in our approach of looking for trace analytes in high-grade ethylene. And we're going to look at a new technology, online GC-MS, MS being mass spectrometry. We're going to assume that we have a number of people in our audience today that have, say, no GC-MS experience. So why don't we cover the basics of GC mass spec, talk about the unique strengths of this detector and the output of mass spec is spectra. We're going to look at some example spectra of analytes that we're interested in. Lastly, we're going to look at a case study of a monomer analyzer. This detector, this GC uses three detectors: mass spec detector, a PDHID, and an FID. The problem, impurities in ethylene streams are very costly. They impact the final product. And if you're impacting the final product, then you're adjusting the price that you can get for that product. Quality goes down, price goes down. How the product impacts the catalyst is also of critical importance. Bad ethylene is going to decrease catalyst efficiency. It's going to reduce yields. The inverse of that means it's going to cost a lot more to maintain your plant, and it's going to cost more for frequent catalyst replacements. All of those not good things. Limitations of the current approaches. So these might be classical process GCs that you might find out on the market today. These guys are typically providing at ppm level detection, and as we're out there in the ethylene spec wars, we want to be lower and lower with respect to detection limits of any impurity that we want to quantify. The lower we can spec, the more money we can get for our product. They mainly rely on isothermal ovens and packed columns, older technology. Many lack detectors required to go below the ppm, and often only a few analytes per analyzer. So that means we're going to have a series of analyzers in our shelter, each one addressing a portion of the sample list that we're talking about. Lab GCs are great, but they're stuck in the laboratory. They can't measure in real time. We have to wait for an operator to go out, grab a sample, transport it back to the laboratory, wait for the sample in the queue, then it gets measured. At some point later in time, we have to wait for the results. Variable integrity of grab samples, that means as we're capturing that sample from the line into a sample bomb and we're transporting it, it may be reacting with itself inside the bomb, it may be reacting with the bomb, and by the time we get back, the integrity or the actual chemical composition of that sample may in fact have changed. Then we've got to deal with variable operator expertise. So the sample gets back to the lab, it needs to be run on GC or GC-MS, and that's going to be plus or minus that operator, and whether or not that person's having a good day or a bad day, that's not good for us. So what's our approach? Our approach is to use the combined power of GC mass spectrometry plus a couple of other detectors to produce something that's really sensitive and comprehensive. So sensitivity, we need to go down to the part per billion range. A lot of these catalyst poisons are really effective, and people are quite interested in knowing exactly what those levels are. Mass spec can do that. It has a broad dynamic range of 10 to the 6th. We're looking for something which is flexible, almost a universal detector. For mass spec, we can do everything except hydrogen and helium. So while those two molecules are very light for the 99.99% of the world we need to address, mass spec is essentially a universal detector. We're excellent tool for troubleshooting. So we like to say, do we have any fill in the blank? So 3 o'clock in the morning, customer calls up and says, hey, we think you've got X in your sample. Say it's acetaldehyde. We think we've got that in your sample that you're selling us, and that's going to be a problem for us. Are you checking for acetaldehyde in your streams? How do you know it's not there? That would be easy for us. We'd go to the library, we'd punch up some trace masses that are indicative of acetaldehyde. We'd add that to our method. We'd quickly run the sample and scan across it and see if we have anything that matches up. If we have something that matches up, then we're going to have to say, wow, I need to go out and build up a calibration blend for acetaldehyde and quantify it. But if in fact I run through that sample and I see the mass spec data does not indicate acetaldehyde, I can say to the customer, no, we've checked this with actually online GCMS, and we find we have none of that in our sample. So we have a very strong analytical position with respect to the quality of our product and what we believe that to be. Online GCMS, it is unambiguous. We don't want to be guessing which peak is which. We want to know for sure. We want to have the ability to essentially look inside each peak and look at the molecular structure that's being used to generate those peaks. So we have a confirmation of each analyte by agreement between molecular ion, the fragmentation ion pattern that we'll look at in a second, and the retention time. So those three components together wipe out ambiguity, no guesswork. Let's look at the basics of GCMS. So this is a simple diagram that we captured. We've got our helium carrier gas. Our system is going to be plumbed online, so we need to have an injection valve so that we can automate the injection. So the valve and the splitter then onto the top of the capillary column. Capillary column is in a GC oven, which is temperature programmable. That's good. Capillary columns are very efficient at resolving complex mixtures. Effluent from the capillary column goes out into the mass spec detector. And the first stop in that mass spec is the ionization source. The ionization source is simply a hot filament. It's heated up to the point where it's glowing. It's spitting off electrons. And the electrons are shooting across the vacuum. And as soon as the molecules elute from the tail of that capillary column, they are bombarded by the electrons and they fragment. Fortunately for the mass spec science, molecules always fragment with the same pattern. So for example, if we had a methanol molecule come from the tail of that column, we'd bombard it with electrons, we'd fragment it. One of the major fragment masses is mass 31, indicative of methanol. But we're going to collect all of those mass fragments and propel them with electromagnets towards our detector element. Our detector element is simply an electron multiplier. That's a device that has a very high voltage applied to it. It's just waiting for a little bit of kinetic energy to avalanche electrons and cause enough current that could be picked up by our data analysis system. So we're generating fragments, we're shooting them towards the detector. In between the two, we have our mass analyzer, and this is a quadrupole. Quadrupole has two electrical fields, one DC, one RF, and they're oriented at 90 degrees. Those two fields are manipulated by the computer associated with that mass spectrometer. And basically, we can tell through the computer the quadrupole to set up so that only a particular mass of interest is allowed to traverse through the quad and hit the detector. For example, if I was looking for methanol, I would tell my quad, let only mass 31 come through the quadrupole and hit the detector. The detector is switched on for X amount of time, and I'm going to gather the number of methanol fragments, or one might say the abundance of the methanol fragments, and feed them towards my data system. When I'm done with mass 31, I would reprogram it in an instant to look for mass 32, then after that mass 33, then after that mass 34, or 43, or 45. That way I would step through my entire list of mass fragments that I'm interested in, and I would be quantifying the abundance of each mass fragment. So if I'm looking at the data analysis at the bottom of this diagram, my top structure is just a two-dimensional chromatogram. It speaks as a function of retention time. But down below that, I have what might be called a series of bar graphs. Each of those bars represents a mass of interest to me, for example, 31, 43, 78, etc. Each of those bars is an individual mass, and the height of each of those bars indicates the relative abundance. So when I'm looking for a molecule, I'm looking for a certain pattern of fragments or masses, and I'm looking for a relative abundance between those fragments. So it's like I'm generating actually a series of chromatograms or chromatograms in 3-dimension. If I have a TCD or an FID, all I get is peaks as a function of retention time. That's just 2D. But with the mass spec, I have a series of chromatograms. Each chromatogram generated is a function of the mass that I'm looking for. So I can look for the intact parent molecule. I can look for each fragment of interest to me. And I can also look and make sure that I'm logging the constant ratios of those fragment abundances. All fragments from the same molecule have the same retention time. So basically, I'm collecting all of these chromatograms. Each one is a function of a mass, and I can go in and individually look into those, generate separate chromatograms, and use that for quantification. We'll look at that in a second. Let's look at two molecules that are very close in structure, 2-chloropropane up on top, 2-chloropropene down at the bottom. You can see the structure on the left, they're very similar. If I injected those onto a column, perhaps a DB1, I might expect those two components to have the same retention time. If I had an FID, that's going to be a problem because now I can't quantify them individually, and that's what I need to do. Mass spectrometer, though, that's different. Look at the mass spectrum of the 2-chloropropane up on top. My major fragment for 2-chloropropane is mass 43, and my parent is 78. My 2-chloropropene, my major abundance is 41, and my parent is 76. So if I have the ability to draw a chromatogram of mass 43 and a separate chromatogram of mass 41, you can imagine that I've got completely different chromatograms related to each of those compounds, even though they have the same retention time. Hydrides are very important as being catalyst poisons. We're often looking down in the part per billion range. So arsine up on top, we've got a major mass at 76 and a parent at 78. Down below, same family, but a completely different spectrum. And this phosphine spectrum, our parent is at 34. We'll use that for quantification. Oxygenates, also catalyst poisons, so we better look at those. We've got methanol and acetone. The methanol up on top, remember there's our mass 31 that we were talking about earlier. So we'll use that for methanol. Down at the bottom, acetone, completely different. Major at 43 and a parent at 58. Now let's look at a difficult situation. I've got a whole list of analytes that I want to address, two of which are methanol and diethyl sulfide. And the column that I've chosen really does well, except for methanol and diethyl sulfide. As you can see from the chromatogram on the left, in fact, those two guys have the same retention time. That's not going to work for me. So what I do is I go to my mass spec, the database that comprises my GC run, and I say pull out or extract iron 31 and draw me a chromatogram of only iron 31 or mass 31. That's the chromatogram we see up on top. Down below, I can say, okay, now go back to the same run, same database, and extract out iron 75. That's going to be the chromatogram that's on the bottom. So now I've taken two co-eluting peaks, but I've generated independent chromatograms. The methanol peak, I can integrate that, I can calibrate it, I can use that to generate a methanol quantification number. Down below, I can take the diethyl sulfide peak, I can integrate that peak separately, I can calibrate it, and I can use that to generate a diethyl sulfide result. Now let's look at the case study of a monomer analyzer here that seems to be able to fit the whole bill, mass spec, PDHID, and FID. Here's a picture on the right that we want to look at. Down the bottom, we've got our mass spectrometer. We use an Agilent 5977B, probably the world's most popular mass spectrometer. Above that, we have two independently programmable, independent, true convection programmable ovens. So we can put capillary columns in there, and we can get the same type of temperature programming capability that we can in our lab systems. We have a small isothermal oven that sits on the right. Above the two temperature programmable ovens, we have an oven with the cover removed so that you can look on the inside. At the left, we've got our pulse discharge helium ionization detector, PDHID. We've got our FID on the right. In the middle, we've got a series of valves, but these valves are not used for injection because the injection valves are out on the sample system. These valves are used for column selection, back flushing, and arc cutting as necessary in the different applications. Let's look at the plumbing diagram. This diagram is complex. It incorporates both the sample system on the left and the GC analyzer on the right. Let's make things simple and just look at the sample system. The sample system has an array of stream selection valves across the middle of the diagram. In ethylene analysis, we're going to be looking for some things that could also be found in the atmosphere, CO, CO2, oxygen, nitrogen. So we want to have a zero leak valving system, so we use diaphragm valves in this case. Over on the right side, we've got four independent gas sample injection valves. So we push the sample through those valves, essentially capturing 4 aliquots of exactly identical, same sample. The top 2 inject onto a PDHID subsystem, valves and columns and pulse discharge detector. The middle valve, valve 3, it injects onto columns that are targeted, connected to the mass spec detector. Down in the 4 at the bottom, we've got another gas sample valve. It injects onto a columns connected to an FID. Now let's look at the analyzer itself. So the green lines and valving up on top, that's associated with the PDHID. So that's good for fixed gases, hydrogen, oxygen, nitrogen, CO, CO2, things of this nature. In the midsection of the diagram, we have the columns associated with the mass spectrometer. The mass spectrometer is associated with 2 columns. There's a column on the left targeted towards light components. There's a column on the right targeted towards mid and heavy components. With those 2 columns in my analyzer already connected to the mass spec detector, I have a very powerful, broad-ranging analytical capability. I can do lights all the way up to heavies. That detector is going to be used to capture oxygenates such as methanol, sulfurs, mercaptans, H2S, COS, arsine, and phosphine. Down in the bottom, we've got our 6-port valve and 2-column configuration connected to an FID, so we're going to generate speciated C1 to C4 hydrocarbons plus C5 plus. Now let's look at some chromatograms. So this is coming from the mass spec detector. We've got the methanol mercaptan, peak number 3 is ethyl mercaptan, 4 is critically important, it's a very popular COS, 5 is H2S, 6 and 7 are arsine phosphine. We have excellent sensitivity down in the part per billion range, as indicated by the table in the upper right. Look at those peaks. Those peaks are very narrow, sharp, tall. That means good resolution, no confusion with any other peaks in the chromatogram, and because the peaks are narrow and tall, we have excellent sensitivity, very good peak shape. At the same time that chromatogram is evolving, our FID is also generating the hydrocarbon peaks. So peak number 1 is our C5 plus backflush peak. Then we're going to do methane, ethane. After the ethylene matrix, we've got propane, propylene, acetylene, propadiene, isobutane, and N-butane. Again, while those 2 chromatograms are evolving, we actually have a 3rd chromatogram evolving. That means we're doing maximum number of analytes in the minimum amount of runtime. Runtime is typically 10 minutes because we're doing things in a lot of parallel. So if we look at the chromatogram section, at the left, we've got hydrogen, oxygen, argon, nitrogen, methane, and peak number 5 is critically important. That's carbon monoxide. Over on the right, we're looking actually for only peak number 8, which is carbon dioxide. So you can see that we have excellent sensitivity, again, down the part per billion range. Look at especially peak number 5, carbon monoxide, and peak number 8, carbon dioxide. Some people would be tempted to put these 2 analytes through a methanizer. The problem with that is that the methanizer, the nickel catalyst, is going to start to tail those peaks. As soon as you start to tail small peaks, you automatically increase the lower detection limit. That's not good. We look at these chromatograms and we say excellent peak shape. We're well suited to go down into the part per billion range. So in summary, Process GC overcomes a lot of the challenges of monitoring part per billion level impurities in polymer grade monomers, ethylene and propylene. So because we're prompt online, we're maintaining sample integrity. We don't have to wait for the time lag and possible sample corruption, sending samples back to the laboratory. Increased measurement precision. It's a fully automated system. It does the same thing over and over again. That tightens our precision index. GCMS, except for hydrogen and helium, it's a universal detector, which is good. We can apply it to the list of analytes we've got today, but if something pops up next month, next year, we can easily add that to the list, modify the methods, and away we go. It's very sensitive, easily down the part per billion, and it's got excellent dynamic range of 10 to the 6. Unambiguous, that's what we like when we're talking about online analytics. We don't want any confusion, we don't want any guesswork. It's like being able to look inside the peaks generated by a mass spectrometer. We can look at the peak, the parent ion, and the fragment ions, and we know exactly what we're looking at. It's very adaptable. Like we said a second ago, if something pops up, it's easy to add something to a mass spec detector because it is virtually a universal detector and also very sensitive. Okay, thank you for your time today. If you have any questions, and perhaps if we can't get to them right now, my email's up on the screen. Simply jot that down, and at any time, your convenience, send your questions to me. We'd be glad to work together with you.